I chose problem 3 from 2006 because it's another example of where we have to use I alpha and RF sine theta, that relationship for rotation. I also did this for the general case if you're not given I, so I will have to make adjustments to my answers here because they actually tell you that you're dealing with a thin hoop with a rotational inertia of mr squared. Okay, so it starts up at the end of a ramp, it's going to go down to the ramp, and then it's going to roll on a table horizontally, and then it's going to go off the table. Okay, first thing they're asking you to do is derive an expression for the acceleration of the center of mass of the hoop as it rolls down the ramp. So we're going to use our relationship right here again. The torque is equal to I alpha, or RF sine theta. In this case, the force of friction is what's causing the rotation. If you forgot, we actually did this in class. We did this straight derivation in class, so please check your notes for that chapter. We remind ourselves that alpha is equal to A over R, so there's that linear acceleration that we want to try to find. That's the acceleration of the center of mass, is equal to R times the force of friction. So I'm solving for the force of friction here as I times A over R squared. Okay? Then we treat this as a mass on top of an inclined plane. So if the object goes down the inclined plane, it has its mass times its acceleration is the net force. That's going to be the difference between mg sine theta trying to take us down the inclined plane and the force of friction trying to take us up. We don't know what this force of friction is. Remember, it's static friction, but we don't know the maximum value of it. So I need to replace that with what I found up here, IA over R squared. Okay? So now we bring the IA over R squared to the other side because I have the acceleration in both of these terms. I'm going to rip an m out of this, and I'm going to get that the acceleration is equal to g sine theta over 1 plus I over mr squared. Now this is the general case. They gave you that it's a hoop, so it's mr squared for I, so that's why the answer in the actual notes is g sine theta over 2. Okay? But I'm doing this for the general case. Part B, derive an expression for the speed of the center of mass of the hoop when it reaches the bottom of the ramp. Well, the distance traveled is going to be L. I know the linear acceleration, so I'm just going to use one of my big four equations. V squared is equal to V naught squared plus 2A delta x. Delta x is going to be L. We replace the acceleration with what I found in part A. Again, these problems over and over again use previous examples in previous parts when you're proving a new part. And so we get the V squared is equal to 2 times g sine theta over 1 plus I over mr squared. Again, this I would be replaced with mr squared since we are given the fact that it's a hoop. So the 2's would cancel out. And that's why the book's answer is the square root of g sine theta times L. Okay? Derive an expression for the horizontal distance from the edge of the table to where the hoop lands on the floor. Everybody make sure you have this. Pause it. Get it down in your notes. Now I immediately got nervous on this one because I thought that it was falling directly off the table, so I was going to have to split it into components. But thankfully the hoop goes on the table and then rolls off. So that velocity that you found in the previous part is now directly horizontal. So it just becomes a horizontal object falling off a table. We've done those problems a million times before. You know the height of the table, you know the initial velocity in the y direction is 0. So h is equal to 1/2 gt squared. So we get a time in the air of 2h over g square root. Trying my best not to sneeze. And then the horizontal distance traveled will be the horizontal velocity times that time. So I get 2g sine theta L square root sine over 1 plus I over mr squared. Again, that I is mr squared multiplied by 2h over g. Again, I did the general case. You'd have to replace I with whatever object you're given. Speaking of which, suppose that the hoop is now replaced by a disc having the same mass m and radius r. How will the distance from the edge of the table to where the disc lands on the floor compared with the distance found in part C? Since we have a smaller I, you have a smaller rotational inertia for a solid disk. If you don't believe me, look it up. It's 1/2 mr squared. Since you have a smaller I, that means down here in the denominator, this is going to be a smaller value. It's going to be smaller than 1, which means that the velocity is going to increase, which means that this is going to go further in the horizontal direction. Smaller I means a smaller number down here, and since it's a smaller number down here, that means that it's going to go further. That's not very intuitive, so make sure to check your notes on those rotational inertias and recognize that the rotational inertia is in the denominator and it's going to be smaller than this example.